start the another topic, that is the packing fraction. That is a packaging in the different, not packaging fraction actually, it is a packaging in the different dimensions, that in which we learn firstly the packaging in 1D, one dimension. How the packaging in one dimension will be takes place? The packaging in one dimension will takes place like this. Here is a layer, that is a layer. Here we consider any atom, like this is the one of the atom of it. So and ask someone like the coordination number of it, coordination number of it. The coordination number of it is 2, because it has in 2 neighboring atom only, so its coordination number is 2. As we move ahead, then that is packing in 2D. Packing in 2D. In packing in 2D, there was the first thing that we have to study. There was a different type of packing in 2D. That is, first of them is square closed packing. In a square closed packing, there was a 2-dimension thing. So here this kind of scenario will exist. Okay, I will make it once. This. Yeah, this kind of thing will happen. A, B, C and D. Okay, so how we can able to calculate what are the terms which is used here? Okay, first thing which is asked there is what is the pattern used here. Actually this is a layer, and this is also a similar kind of layer, so it is a layer. So which kind of layer is pattern, layer or pattern is used? First of them is pattern used is a type, a type, a layer is used, a type layer is used, a type layer is used. Second question is the unit cell is used here, unit cell is used here. That is, a square shape is formed, so square unit cell, square unit cell used here, square unit cell used here. Third, what is used here, that is C, is Z effective. Z effective is the total number of atoms present in it. So you see there is an atom. Okay, this is the atom, how many part of it was contributing to this unit cell? That is 1/4 part. And how many atoms involved for this unit cell? There was a 4 atom involved in it, and each of them contributed 1/4 part of it. So unit cell. So Z effective is 1. D is the coordination number. Coordination number is how many through a single atom. If we consider a single atom like this is a single atom that we consider. So how many neighboring atom of it was? That is, this is the neighboring atom, this is the neighboring atom, this is a neighboring atom, and another a layer maybe was existing there. So that atom is also its neighboring atom. So coordination number of it will be 4. So and now a part is, another question will be maybe asked, that is 2r, that is a, that is the relation that here exists, that we easily find, that is the distance between that, this is a, and that is the distance between their 2 radius. Okay, now the another thing that is the important thing, that is a packaging fraction in it. That is packaging fraction in 2D. Packaging fraction in 2D's formula was different from the packaging fraction in unit cell, that is Z into area of the disk. Disk is like this is a disk by area of the unit cell. That is, here we have the square unit cell, so we use the square. So this is how, what is the Z effective of it is 1. What is the area of disk? That is pi r square. What is the area of unit cell? That is equals to a square. What is the relation between them? That is a equals to 2r. Then it is equals to 1 into pi r square. A equals to 2r, that is 4r square. This is equals to pi by 4 into 100. Okay, here 100 I miss, so into 100 into 100, so into 100, then it come to be 78.5%. 78.5%, that we have to remember. So this is the packaging fraction, means the space on which the atom was really present in the unit cell. And so the void present in the unit cell is void present, G, void in unit cell is 100 minus 78.5%, that is 21.5%. I will discuss this unit cell, that is square closed packing unit cell, in very detail, so that you do not get bothered when I leveling up to another while discussing the another kind of packaging in 2D, that is a hexagonal closed packing. That is another is hexagonal closed packing, that is called SCP. Here we can this called SCP, the square closed packaging, and here is a hexagonal closed packaging. Here which kind of layer is present? Here I will discuss the layer type present. This is A layer, this is B layer, and this is again A layer. Why we tell it's a B layer, it's a A layer? Because see, the A layer are similars and B layer are different, because the B layer is present on the voids of the A layers. Okay, this is the difference that's through which we can differ easily. Okay, here we do the hexagonal, this this and this. Okay, this is the hexagon that we can draw, and the part that it will cover. Okay, there is a hexagonal closed packing. The pattern is used here is AB, 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 and it was keep continuing. B is the unit cell. The unit cell used here is hexagonal 2D or hexagonal closed packing. Third C is Z effective. Z effective of it is 3. You can calculate by yourself by knowing how I can calculate for the square plane for the square closed packing. D is coordination number, that is 6. A is the relation between A and R, that is 2R, that is equals to A. And it's again, and last thing is packaging fraction, percentage of packaging fraction, that is Z into area of disk by area of unit cell into 100. Okay, so how we can calculate it? Of course, we have to know the area of it. The area of hexagon is nothing but the area of hexagon is nothing but the area of 3 by 4 a square, that is area of what? The area of the equilateral triangle into 6, that is if there is a if you take the hexagon of equal, that is regular hexagon, so this is the triangle that is of equal length, that its area is root 3 by 4 a square. These kind of 6 triangles present in it. Okay, so we can easily write the area of hexagon through it, that is nothing but the area of the unit cell. Okay, now we will going to there is the end of the packaging fraction. Now we will easily going to move for the 3D packaging. This is the end up with the 2D packaging. Now we come to move forward to closed packing in 3D. Okay, first is square closed packing, that is in 3D. From from 2D, from 2D square packaging, from 2D square packing. Okay, so here are also the all the elements that we have to study. That is, first of them is the arrangement. Through arrangement, firstly we have to understand which kind of unit cell is used here. Okay, here also a type is used, both layer is a layer. Okay, but here the 3D is because the layer upon layer is present, means above this layer or above layer, the layer is present, and below this layer is present. Means if we consider this layer, so above this layer a layer was also present, and below this layer another layer is all present, but that having the similar property, because all of them are overlapping and having similar kind of behavior as the layer A. Okay, now we come to know what is this. Okay, yes, here the arrangement is AA. Okay, there is a unit cell is used, that is the simple cubic. The Z effective, we can easily calculate what is the Z effective of it. Z effective of it is how many atoms involved, 4, and how many parts, that is 1. So Z effective is 1. And coordination number, how many negating atom of it is 1 2 3 4, and upper wala, that is 5, and niche wala, that is 6. There is 6 number of atoms which is present here. And another is the relation between A and R, 2R, that is equals to A. And we have to learn it having the same packaging fraction that as the simple cubic, that is nothing but 52.4%. that is nothing but 52.4%. Okay, let's move ahead to the another system, that is another packaging system, that is cubical closed packing. (3D). It is formed by the hexagonal closed packaging 2D. Now we move to the another part, that is a cubical closed packaging, that is 3D. That is hexagonal closed packaging, that is composed of the hexagonal closed packaging. How this will be happen, that is I will show you. This is the layer, and on this A layer, there was on this layer there was another layer which is present. On this layer, that is on the voids of this layer, on the voids of this layer, the another layer is present, that is a B layer. And on this there was a third layer is present, that is on the void of it there was a third layer which is present. So here are there are layer A, that is formed from SCP2D. Okay, there was a layer B that is placed in the void of layer A, and that is the layer C, placed in void of both layer A and B. And I am going to tell you that what is introduce another point, that is layer C is placed in placed in the octahedral void of the layer A and B. Okay, so you'll come to know about octahedral void very soon. Okay, from this time we move towards the another one, that is what is its pattern. What are the patterns that we observed here? Pattern that we observe here is A B C A B C A B C, and this kind of layer will be find. There is a unit cell which is used here is unit cell, that is HCP, that is hexagonal closed packing, is used this hexagonal closed packing 2D. In hexagonal closed packing 2D, we use the face center. Unit cell is used as face center. The hexagonal closed packing, the unit cell is used as face centered unit cell. Okay, the Z effective of it is 4, and coordination number is 12, because as it is belongs to face center unit cell, so all the property will inherit to it, that is Z effective of face center is 4, Z effective of the coordination number of face center is 12. Similarly, the relation is also copied from the face center, that is 2r, that is equals to root 2 by 2a. Similarly, the 6 point is packaging fraction of it is 74%. All things will be copied from the face center. There was another important kind of closed packing in 3D, that is hexagonal closed packing in 3D. Hexagonal closed packing in 3D, that is from SCP 2D. Okay, here is a different kind of pattern that is given here. The layer A having the 7 atoms, and layer B having the 3 atoms, and layer C also having the 7 atoms. Layer A is SCP-2D, and layer B is placed over the voids of layer A, and layer C is same as the layer A. You don't able to understand, I have to draw it, I think. Okay, this is the layers, and they overlay, and through this I will going to show you this. This is layer A, and this is under wala is layer C. This is layer B. So and layer A is formed by SCP A2D. Layer B is placed over the the void of layer A. Okay, and layer C is same as the layer A. So that here the pattern is used is AB. Here the another thing, that is unit cell is used, that is hexagonal unit cell, hexagonal unit cell is used, hexagonal unit cell is used. Then there is a Z effective. Is here is 6, and here one of the important thing that we have to remember, that is coordination number. Its coordination number is 12. How its coordination number is 12? Here this kind of structure actually exists, that is this, okay, and then it was this, okay, and then it was this. Okay, so this is the place where the atoms are present. Okay, so number of atoms that is surrounded by another atoms, so we can consider, we can try to consider how many atoms are the neighboring of this atom. So 1 2 3 4 5 6 7 8 9 10 11 12, so 12 atoms are the neighboring of this atom. That's why it having the coordination number is 12. So relation between, and another thing is the relation between R and 2R, that is 2R that is equals to A. And packaging fraction, percentage of packaging fraction, percentage of packaging fraction is same as the percentage of packaging fraction of cubicle closed packing, that is equals to the 74%. But here we have to learn one formula, that is volume of hexagon in 3D. What is the volume? Volume is nothing but the area into height. Area we know 6 into root 3 by 4 a square. What is the height of it? Height of it is nothing but 2 into root under 2 by 3a. That we have to remember. It is the height of the 3D hexagon. Height of the 3D hexagon. Now we move to the another part, that is the CCP and FCC having different kinds of tetrahedral and octahedral voids. How we able to calculate the tetrahedral voids and octahedral voids of the unit cell? First is the CCP and FCC. FCC or secondly is SCP 3D, SCP 3D, yeah, SCP 3D packaging of unit cell. So if number of atom in unit cell is Z, therefore octahedral voids are equals to Z, and tetrahedral voids are equals to 2Z. This is valid for both. Here Z value for the CCP, Z value for the that is cubical closed packing was Z effective. This is Z effective of cubical closed packing was 4, and the Z effective of SCP-3D is 6. So according to which we can easily able to calculate the octahedral and tetrahedral void of the crystal lattice. Okay, now we further move towards the another part of our scenarios, that is the density of the unit cell. What is the density of the unit cell? That is density. Density is nothing but mass upon volume. So how we can find the density of a cell? Density of cell formula is nothing but Z effective into its molecular weight into Avogadro's number Z effective into molecular weight into Avogadro's number into its volume of its cube. How we can able to get it? I know that number of moles, that is equals to weight upon atomic weight into N upon Na. What is this Na? Na is nothing but the number of atoms, and this number of atoms will be considered as Z. That is number of atoms that is considered as Z. That is the Z effective, that is number of atoms which is present in the unit cell. Now we come to know and discuss about the type of voids. First is triangular void. That is how we can represent the triangular void. This is the triangular void. Having coordination number 3. Triangular void is generally found in SCP-2D. Okay, now we move towards another void, that it another void is tetrahedral void. Another void is the tetrahedral void. In the tetrahedral void, the coordination number tetrahedral voids was like that: this, 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 and over that there was an atom. So tetrahedral void are the void on which having coordination number is tetrahedral void coordination number is 4, and tetrahedral void is seen generally found in CCP, that is cubical close packing, and hexagonal close packing 3D. Hexagonal close packing in 3D, and its Z effective is nothing but 6 for SCP, and Z effective is 4 for CCP, that is cubical close packing. There was another close packing, that is octahedral void, that is octahedral void. There the octahedral void is like this, and this, and there's another this, this, this. That is octahedral void. Octahedral void, it having coordination number 6. The octahedral voids are generally seen in generally seen in only CCP and SCP 3D. Okay, and there was a last type of void that is generally seen in only simple cubic cell, that is cuboidal void. This void is generally seen in simple cubic. Its coordination number is nothing but 8. Its coordination number is nothing but 8. Lastly, we have to discuss the size of the octahedral, trigonal, and these all kinds of voids. What are the sizes of the voids? The largest voids is cuboidal void. Then its bigger void is octahedral void. Then the tetrahedral void, and the smallest one is trigonal void. Okay, now lastly we are going to discuss about the location of the voids. Firstly, we come to start with tetrahedral voids. Tetrahedral voids, there are 2 tetrahedral voids on each body diagonal, means it is found in body diagonals. In one body diagonal, there is 2 tetrahedral voids. In one body diagonal, there is 2 tetrahedral voids. The distance between the corners and the nearest points between the corners and nearest tetrahedral void is √3 4 by 8. How it will be? See, this is the cube. Okay, this is the cube, and through which this is the atom. This is the body diagonal through which which we can draw. In this cube we are not able to explain it. Let's give me the another chance to make the another kind of cube and having another body diagonal. Yes, this is the body diagonal that we have, that I can consider. This is the body diagonal that having length, body diagonal length is body diagonal length of cube having side length a is root 3a. Okay, so from this a b c, ab, that is equals to ac, that is equals to root 3a by 2. So as mentioned, there is the distance between the corners and the nearest tetrahedral void is root 3 by a by 4, means one tetrahedral void is present there and one tetrahedral void is present there. So there is two tetrahedral void is present in the one body diagonal, and there is how many body diagonals in the cubical cell, that there is a 4 body diagonals in it. So there is how many tetrahedral voids which is present in it. There was at least 8 tetrahedral voids which is present in the body diagonals of the cubical cell. Okay, now we before moving to the another question, another void, we can, there was another question, famous question which is asked, that is the minimum distance, that is the minimum distance between the tetrahedral voids. The minimum distance between the tetrahedral voids was not root 3 by 2 and root 3 by, it is a by 2. How it was a by 2? Okay, there was a tetrahedral voids was from all the sides. Okay, if a unit cell having these a unit cells of cube having length a of having body diagonal root 3 by a, means root 3 of a body diagonal cube, body diagonal cube having edge length a, so that root 3 by 2a body diagonal cube having side length a by 2, so that is a by 2, that is the a by 2 is the minimum distance between the tetrahedral voids if we make it. Okay, let's think about it, and then if you have any query regarding it, then mention in the comment. I will take it and consider it. Okay, now we will move towards the another part, that is octahedral void. That is octahedral void is generally seen in FCC, and it having face centered cubical closed packing, that is it having two cases, case 1 and case 2, that is it is present at the body center and it is also present at the edge center. S center yeah. It is also present in the edge center. In the body center, in the body center there is octahedral void, that is equals to 1. In the edge center there was 6 edges of the cube. There was 12 edges in the cube. There was a total 12 edges in the cube, but how many of them is contributed to it? That is octahedral void. There was 12 edges, but each edge is contributed to the unit cell, that is 1 by 4th part, that is equals to 3. So therefore total number of octahedral void is 4. Okay, so here we come to end with the location of the voids also. Now we have to study the another thing, that is the radius and the relation of the coordination voids. That is, before coming to that, the point that I wanted to mention in front of you that in a body diagonal there is 3 voids, and there are 3 voids which are present, in which 2 are tetrahedral voids and 1 are octahedral void which is present at the center of it. Okay, now we come to the radius ratios. that is the radius. Another topic, radius ratios, that the ratio of the radius of cation to that of radius of anion. Here the radius ratios are from 0.155 RC by RA, that is radius of cation by radius of anion, to 0.225, from 0.225 RC by RA to 0.414, from 0.414 to RC by RA, that is 0.732, or from 0.73 to RC by RA to 1. Okay, so this is the radius ratios and its coordination number for coming these radius ratios. Coordination number of it is 3, coordination number is 4, coordination number of it is 5, and coordination number of it is 6, and coordination number of it is 8. Okay, so the geometry of it void is, it is a trigonal geometry. Geometry of this is tetrahedral void, this is the octahedral void, and this is the cubical, this is the cubical void, this is the cubical void. Okay, the sum of the example, this is trigonal is example is B2O3, that is tetrahedral voids having example like Z and S, octahedral voids like NaOH and MgO2, that is and cubical void is, that is CaCl. Here, before we further proceed, I wanted to aware you that mostly time the cation is the part of a compound that was present in the void. Why cation? Because as comparatively the size of anion, the size of cation is smaller than size of its anion, means A plus a minus is the size, so that size is smaller, so that it was present in the voids. And there were some exceptions like in CaF2. Here F minus, here F minus is present in the voids. Okay,